Welcome to day 11 of our low-level design course. Today's topic is focused on two important creational design patterns, the factory pattern and the abstract factory pattern. These patterns are pivotal in managing object creation in a flexible, scalable, and maintainable way. Let's dive into understanding both patterns and how they can help us in our system design. By the end of day 11, you will be able to understand the factory and abstract factory design patterns. You will learn how they simplify object creation, making our system more flexible and easier to maintain. We will also explore why, when, and why to use these patterns, and you will gain practical experience in implementing them to solve real world design problems. Today, we will focus on two creational design patterns, the factory pattern and the abstract factory pattern. These patterns help manage object creation while keeping the system flexible and scalable. The factory pattern is used when we need to create objects of different types, and the abstract factory pattern is used when we need to create families of related objects. Let's start with the factory pattern. This pattern provides a way to delegate object creation to subclasses while keeping the object creation details hidden from the client. The factory pattern is used when we need to create objects based on input or conditions but want to hide the instantiation logic. For example, a document creation system can create different document types such as text document or spreadsheets without exposing the class details. The structure of the factory pattern involves several key components. First, there's a product interface, which defines the common behavior for all product types. Next, we have concrete products, which are the actual product classes that implement the product interface. The creator class declares the factory method, while the concrete creator classes implement this method to return a specific type of product. In our document creation system, the first component is the product interface. This interface named document defines the common behavior for all document types. For example, it may include a method like create that all document types should implement. By using this interface, we ensure that all types of documents share a common contract. Next, we define the concrete products. These are specific types of documents such as text document and spreadsheet. Each of these classes implements the document interface, providing their own implementation of the create method. The text document will contain logic for creating a text document, while the spreadsheet will handle the creation of a spreadsheet. Now we have the creator class, which declares the factory method, create document. This method does not specify which document will be created. Instead, it serves as a placeholder for the actual object creation logic. The client code will call this method without needing to know the specific type of document it will get. In the concrete creators such as text document factory and spreadsheet factory, we implement the create document method. The text document factory will return an instance of text document, while the spreadsheet factory will return a spreadsheet. This design ensures that a client code can create documents without knowing the specific class being instantiated. Let's look at the code for the document interface. The document interface declares the create method, which must be implemented by every specific document class. This ensures that each document type shares a common interface that the system can interact with all the document types uniformly. In the text document class, we implement the create method. When called, this method will output a message indicating that a top text document is being created. This demonstrates how the factory pattern allows for flexibility, enabling us to handling different types of documents with their specific creation logic. Similarly, in the spreadsheet class, the create method will output a message indicating the creation of a spreadsheet. By implementing the create method in each document type, we ensure that every document behaves consistently according to the same interface while maintaining its own creation logic. The document factory class declares the factory method create document. This class acts as a blueprint for creating documents, but it does not implement the logic for creating specific document types. It leaves that to the concrete creator class. The text document factory is a concrete creator that implements the create document method. This method returns a new instance of text document. The client code can call this method without worrying about how the text document is instantiated. Similarly, the spreadsheet factory implements the create document method and returns an instance of spreadsheet. This allows the client code to create a spreadsheet without needing to know the internal details of how it's created. The factory pattern has several benefits. It centralizes the logic for object creation, making your code easier to maintain. It also promotes loose coupling between the client code and the concrete product classes. As a result, it's easier to extend the system and add new product types without modifying the existing code. Next, let's move on to the abstract factory pattern. This pattern is used when we need to create families of related objects. These objects share a common interface, but their concrete implementations may vary. The abstract factory patterns helps to ensure that related objects are created together and are compatible with each other. For example, in a GUI system, we might need to create platform-specific components like buttons and checkboxes. The structure of the abstract factory pattern includes several key components. The abstract factory declares methods for creating families of related products. Concrete factories implement these methods to create specific families of products. Each product in the family follows a common interface which is defined by abstract product. Concrete products implement the abstract product interfaces. In our example, we are designing a GUI system for multiple operating systems. The abstract factory GUI factory will define methods for creating buttons and checkboxes. These methods are not tied to any particular platform but ensure that the created components conform to the platform-specific design. The concrete factories such as Win Factory and Mac Factory implement the methods to create platform-specific components. For example, Win Factory creates Windows-specific buttons and checkboxes, while Mac Factory creates Mac-specific components. This decouples the client code from the concrete details of the products being created. The abstract products are the interfaces for the components like button and checkbox. These interfaces declare the common behavior for the components, such as the render method. Each concrete class will implement this method according to its specific platform. The concrete products are the platform-specific implementations of the components. For instance, Win button and Mac button are the concrete implementations of the button interface. Each class implements the render method to display the button according to its respective platform. The button interface declares the render method, which is implemented by each concrete button class. The render method allows the button to be displayed differently depending on the platform. By defining this method in the interface, we ensure that all buttons behave consistently across platforms. Similarly, the checkbox interface declares the render method, which is implemented by each specific checkbox class. This allows the system to handle different platform-specific checkboxes while maintaining a consistent interface. The GUI interface declares the methods for creating buttons and checkboxes. These methods are platform agnostic. It's up to the concrete factories to implement them and return platform-specific components. The Win button class implements the button interface for Windows, and its render method displays a Windows-specific button. By adhering to the interface, the class ensures that it behaves consistently with other buttons in the system. Similarly, the Mac button class implements the button interface for Mac, ensuring that the button behaves according to the Mac design guidelines. This makes it easy to swap between different platforms while maintaining consistent behavior. The Win Factory class is a concrete implementation of the GUI factory. It creates Windows-specific components by implementing the create button and create checkbox methods, ensuring that all components created by this factory are compatible with Windows. Similarly, the Mac Factory class creates Mac-specific components. It implements the create button and create checkbox methods to return Mac-specific products. This allows us to easily switch between different platforms by using the appropriate factory. The abstract factory pattern ensures that related products are created consistently and are compatible with each other. It isolates the concrete product classes, making it easier to switch between different families of products. The unified interface also simplifies the process of adding new products to the system. So what's the difference between the factory pattern and the abstract factory pattern? The factory pattern focuses on creating a single type of product, such as a document or a button. The abstract factory pattern, on the other hand, is used when we need to create families of related products, such as buttons and checkboxes, for a specific platform. We should use the factory pattern when we need to create objects of different types that share a common interface, and when object creation requires specific logic. We use the abstract factory pattern when we need to create families of related objects that must adhere to a set of interfaces and be compatible with each other. For today's exercise, design a furniture store system using both the factory and abstract factory patterns. Use the factory pattern to create individual furniture prices like chairs, tables, and sofas. Then use the abstract factory pattern to create families of furniture such as modern or classic furniture. Be sure to draw UML diagrams and implement that design. Today we explored the factory and abstract factory patterns, two essential tools for managing object creation in a flexible and maintainable way. By centralizing the logic for creating objects, these patterns make your system more scalable and easier to extend. Tomorrow we will dive into the singleton pattern, so stay tuned and thank you for your attention. Welcome to day 12 of our low-level design course. Today we are going to explore two very important design patterns, the singleton pattern and the builder pattern. These patterns are frequently used in object-oriented design to solve real-world problems involving object creation and management. Understanding these patterns will allow us to design more efficient, maintainable, and flexible systems. Let's dive in and see how these patterns help streamline the way we build and manage objects in software design. By the end of today's session, you will be able to understand the core principles behind the singleton and builder patterns, identify when and where to use these patterns in real-world applications, gain hands-on experience through coding exercises which will help you implement these patterns in your own projects. We will also look at potential challenges and pitfalls of these patterns, ensuring that you can apply them effectively. Let's get started with a quick review of where we left off yesterday. Before we dive into today's patterns, let's quickly recap what we have learned yesterday about the factory and abstract factory patterns. Both of these patterns help us create objects without exposing the instantiation logic to the client. This focus on creating families of related objects. Now, as we look at singleton and builder patterns, we will shift focus from object creation to managing object instances and structuring complex object construction. These are equally important in creating clean, maintainable designs. Let's begin with the singleton pattern. To understand the problem it solves, imagine you are designing a logging system for a large-scale application. You want to ensure that there is only one instance of the logger class to avoid inconsistent logging behaviors. If you create multiple instances of the logger, it could result in duplicate logs or even performance issues due to unnecessary object creation. The singleton pattern is designed specifically to address this problem, ensuring that a class has only one instance and providing a global point of access to that instance. The singleton pattern ensures that a class has only one instance and provides a global point of access to that instance. This is achieved by making the constructor of the class private, preventing direct instantiation. Instead, a static method is used to return the single instance of the class. It's typically used in scenarios where having multiple instances of a class would lead to undecidable outcomes, such as in the case of a configuration manager, database connection pool, or logging system. The singleton pattern is perfect for ensuring global consistency and saving resources in your system. There are several ways to implement the singleton pattern, each with its own advantages and trade-offs. Let's go over a few common approaches. Lazy initialization. In this approach, the instance of the singleton class is created only when it's needed for the first time. This is efficient in terms of memory usage. Thread-safe singleton. When working with multi-threaded applications, ensuring that only one instance is created is crucial. In a thread-safe singleton, additional synchronization mechanisms like locks or mutexes are used to ensure thread safety during the instance creation. Eager instantiation. The instance is created when the class is loaded and no further synchronization is needed. This approach is simple but may be less efficient if the object creation is resource intensive. Build path singleton. This method uses the initialization on-demand holder idiom, leveraging the class loader mechanism in Java to ensure that the singleton instance is created lazily but safely. To see the singleton pattern in action, let's look at a few real-world examples. Logger systems. Often we need a single centralized logger that handles all log messages throughout an application. Having multiple instances of the logger could lead to inconsistent log messages. Database connection pools. A connection is a limited resource in your application. You don't want to create new connections every time you need one. So a singleton connection pool manages all the database connections, ensuring there's only one instance of the pool. Configuration managers. Many applications have configuration settings that need to be accessed globally. Using a singleton ensures that the configuration is loaded only once and used consistently throughout the application. While the singleton pattern can be very powerful, it's important to use it wisely. There are a few common pitfalls to watch out for. Hidden dependencies. Other parts of your code may become tightly coupled to the singleton instance, making it difficult to test or modify. Global state. The singleton instance represents a global state, which can be problematic in multi-threaded environments if not implemented carefully. Difficulty in unit testing. Since the singleton enforces a global instance, it can become challenging to write unit tests that isolate the behavior of components. Best practices include minimizing the use of singletons, keeping the patterns encapsulated, and ensuring that dependencies are injected rather than directly accessed. Now it's time for you to implement a singleton pattern. Your task is to create a singleton logger class. Try to implement it using lazy initialization first. Once you have completed that, experiment with making the implementation thread safe. This exercise will give you practical experience in applying the singleton pattern and understanding its nuances in different environments. Now let's shift focus to the builder pattern. Suppose you are designing a pizza builder. A pizza might have a number of optional toppings like cheese, mushrooms, olives, and others. Without the builder pattern, the code could quickly become messy with multiple constructors or methods that take numerous parameters. This leads to confusion and lack of clarity in object creation. The builder pattern solves this problem by allowing us to construct complex objects step by step, and more importantly, it makes the code cleaner and easier to understand. The builder pattern separates the construction of an object from its representation. It lets us create an object step by step using a builder class. The builder class defines the different steps in constructing the object, while the product is built progressively, giving us control over the construction process. The builder pattern is especially useful when you have an object with many optional parts or when the object creation process is complex and needs flexibility. Here's the structure of the builder pattern in UML. You will notice that we have the director class which manages the construction process. It uses the builder interface to call the appropriate methods. The concrete builder implements the builder interface and defines the exact steps of building the object. Finally, the product class represents the constructed object. This clear separation of concerns is one of the strengths of the builder pattern, making it easy to manage complex object creation. Let's walk through an example of how the builder pattern works. Imagine you are building a house. You might have a house builder class with methods like add room, add garage, and add swimming pool. Instead of passing all the possible components to a constructor, the house builder allows us to build the house step by step. Once you have finished adding the components, you can call .build to construct the final house object. This makes the object creation process more intuitive and flexible. Real-world examples of the builder pattern include string builder in Java, which allows us to efficiently build strings without creating multiple immediate string objects. Similarly, HTTP request builders in libraries like OKHTTP let us create complex HTTP requests with many parameters like headers and body data. Another great example is UI frameworks where components like buttons, text fields, and layouts are constructed using a builder, making UI creation both clear and flexible. Let's try out the builder pattern in practice. Your task is to create a pizza builder. This builder should allow customers to customize a pizza by selecting different sizes, toppings, and sauces. The director class will manage the pizza creation process and provide several predefined recipes. This exercise will give us hands-on experience with the builder pattern and show us how it simplifies object construction. Before we wrap up, let's quickly compare the singleton and builder patterns. The singleton pattern focuses on ensuring a single instance of a class and controlling global access to it. It's ideal when you need a single shared resource like a logger or configuration manager. The builder pattern, on the other hand, is focused on constructing complex objects step by step. It's perfect for objects with multiple optional components and helps maintain clarity in object creation. These two patterns solve different problems but are both crucial tools in any software design's toolkit. For today's assignment, I have three tasks for you. Implement a database connection manager using the singleton pattern. Create a computer builder that allows the configuration of a computer with different components like CPU, RAM, and storage. Reflect on the drawbacks of the singleton pattern and write about scenarios where its use might cause issues in a design. Complete these exercises to reinforce your understanding of both patterns. Let's summarize what we have learned today. The singleton pattern ensures that a class has only one instance and provides global access to it, making it great for shared resources like loggers. The builder pattern allows for flexible, step-by-step construction of complex objects, making it ideal for objects with multiple optional parts. Both patterns play a vital role in designing robust and scalable systems. Keep practicing and you will soon be able to recognize where and how to use these patterns in your own projects. Thank you for your attention. Hello and welcome to day 13 of our course. Today we are going to explore two powerful design patterns, the prototype pattern and the object pool pattern. Both of these patterns play a crucial role in improving the efficiency of object creation and resource management in your system designs. Let's dive right into the understanding what these patterns are, when to use them, and how they can make your designs more efficient. By the end of this session, you should be able to understand both the prototype and object pool patterns, know when to apply them, and be familiar with their real-world use cases. We will also dive into some practical coding examples so you will get hands-on experience with these patterns. So let's start by looking at the core goals of today's lessons. Let's begin with the prototype pattern. At its core, the pattern is all about cloning objects rather than creating new instances from scratch. Picture this, you have an object with a certain state and you need many similar objects in your system. Instead of recreating the object and setting all the values again, you simply clone it. This pattern is ideal when object creation is costly in terms of resources or time, such as when constructing objects with complex states. In this pattern, we define a prototype interface, usually with a clone method. The concrete classes implementing this interface will provide their specific implementation of the clone operation, allowing the system to quickly generate similar objects. So why and when would you use the prototype pattern? This pattern is particularly useful when you need to create a large number of similar objects and the process of creating each object from scratch is expensive or complex. For example, in a game engine, you might have various types of enemies, all having similar attributes like health, speed, and strength, but each instance may vary slightly in these attributes. Instead of recreating each enemy from scratch, you can clone an existing one and adjust only the differences. The prototype pattern saves time, avoids repetitive initialization, and minimizes the overhead of creating identical objects over and over again. But remember, implementing deep copying for objects with complex states can sometimes add complexity. So it's important to evaluate whether this pattern is the right choice based on your system needs. Let's look at a simple code example for the prototype pattern. Imagine we have a shape class that is the base class for different shapes like circle and rectangle. Each shape has a clone method and different shapes provide their own implementation of how they should be cloned. In this example, the circle class overrides the clone method to return a new instance of a circle with the same properties. This way, instead of creating a new circle object from scratch every time, we can simply clone an existing one and modify the necessary properties such as the radius. This approach ensures that we save time and resources, especially when creating multiple instances of similar objects. It's important to understand the difference between deep copy and shallow copy when working with a prototype pattern. A shallow copy creates a new object but does not copy the objects referenced inside the original object. Instead, the references to these nested objects are copied. meaning changes to the nested objects can affect the original object. On the other hand, a deep copy creates a new object and also recursively copies all the objects inside it, making the new object completely independent of the original object. This approach ensures that no unintended changes can occur between the original and the cloned objects. While deep copying can be more costly, it ensures complete independence of the objects. Now let's move on to the object pool pattern. This pattern is focused on resource management. The core idea is to maintain a pool of reusable objects instead of creating new ones each time they are needed. Imagine working with expensive resources like database connections or network threads. Creating these objects repeatedly can lead to performance bottlenecks and increased memory usage. The object pool pattern solves this by keeping a pool of objects that can be reused when needed. If an object is available in the pool, it's returned for use. Otherwise, a new object is created and added to the pool. Once the object is done being used, it's returned to the pool for future reuse. This way, expensive operations are avoided and resource management is much more efficient. So, when is the object pool pattern most effective? This pattern is perfect for scenarios where object creation is expensive, such as in cases where you are dealing with database connections, threads, network connections, or large objects that require significant initialization. Rather than repeatedly creating and destroying objects, we can reuse them, which reduces overhead and improves performance. However, the object pool pattern does introduce the need for proper management of the pool. If objects are not returned correctly or they become stale, it could lead to memory leaks or degrade performance. It's crucial to ensure that the objects in the pool are properly reset and ready for reuse. Here's a code example that demonstrates the object pool pattern. In this case, we have a connection class and a connection pool class that manages a pool of available connections. Whenever we need a connection, we simply request it from the pool. If a connection is available, we use it. Otherwise, a new connection is created and added to the pool. When we are done with the connection, it's returned to the pool for reuse. This pattern minimizes the overhead of repeatedly creating and destroying connections, making the system more efficient. When working with both the prototype and object pool patterns, there are some important best practices and pitfalls to be aware of. For the prototype pattern, always ensure that your cloning method handles all the fields correctly. If your object contains mutable fields, you should implement a deep copy to avoid unintended changes to the original object. For the object pool pattern, it's essential to reset the state of objects before returning them to the pool. This prevents issues where objects could retain old states and cause bugs or inconsistent behavior. Additionally, managing concurrency is critical. If multiple threads are accessing the pool, make sure access is thread safe. Let's look at some real-world scenarios where these patterns are used. For the prototype pattern, game development is a classic example. Imagine a strategy game with different units like soldiers, tanks, and airplanes. Each unit has similar properties, but their individual attributes differ slightly. Instead of creating new objects from scratch for each unit, we can clone an existing one and modify the specific attributes. This saves a lot of processing time and memory. For the object pool pattern, consider a web server managing database connections. Instead of opening a new database connection for each request, the server can pull from a of pre-established connections, thus significantly reducing the overhead of connection establishment. Another example could be thread pools in multi-threaded applications where threads are reused rather than constantly created and destroyed. Now let's put your learning to the test with a hands-on practice exercise. For the prototype pattern, your task is to implement a prototype manager that can manage a collection of prototype objects, allow for cloning them, and modify their properties when necessary. For the object pool pattern, try building a simple string buffer pool. This pool will manage reusable string buffers that can be reused across different operations. This exercise will give you a concrete understanding of how both patterns work in practice. For your homework, I would like you to design a document editor where both the prototype and object pool patterns are used efficiently. The editor should allow cloning of document pages and it should manage reusable objects like spell checkers or text buffers using the object pool. Also think about the trade-offs involved with deep copy versus shallow copy and consider the risk of having slayed objects in the pool. In summary, today we explored two critical design patterns: the prototype pattern, which helps us clone objects instead of creating them from scratch, and the object pool pattern, which allows us to reuse expensive objects rather than recreating them. Both patterns help optimize resource usage and improve system performance. Tomorrow we'll move on to explore the adapter and breach patterns, two more patterns that will help us design flexible and maintainable systems. Stay tuned and thank you for your attention today. Welcome to day 14 of the low-level design course. Today we will focus on two powerful and essential structural design patterns, the adapter pattern and the breach pattern. Both of these patterns are aimed at making our system more flexible, decoupled, and extensible. These patterns are vital when we are building systems that need to interact with other components or evolve over time. Let's dive right in. By the end of today's session, you should be able to understand the purpose and structure of both the adapter and breach patterns. Know when and why to apply each pattern in your system design. See how these patterns work through UML diagrams and real-world examples. Finally, we will have a practical coding session to reinforce these concepts. So let's start by setting the stage with a quick review of structural design patterns. Before we delve deeper into the adapter and breach patterns, let's first recall what structural patterns are. Structural design patterns are used to simplify the way classes and objects are structured. These patterns help define relationships between different objects or classes, making it easier to organize and scale the system. The adapter and breach patterns both fall under this category and focus on improving flexibility, modularity, and extensibility in your designs. Let's begin with the adapter pattern. In simple terms, the adapter pattern allows us to convert one interface into another that is expected by the client. Think of it like a plug adapter we use when traveling to a foreign country. It allows us to plug our electronic devices into an outlet with a different shape or voltage. Similarly, in software, the adapter pattern acts as a bridge between incompatible systems, allowing them to communicate with each other without needing to change their internal implementations. This pattern is typically used when you want to reuse an existing class but its interface is incompatible with the rest of your system. Now, when would you use the adapter pattern? You should consider using it in scenarios where you have an existing system and you need to integrate a new system or component without modifying the existing code. A common case for using the adapter is when you are working with legacy systems that were developed before your new implementation, and you need to connect them without disrupting the overall architecture. The adapter pattern helps maintain the stability of the existing code while allowing you to integrate new functionalities seamlessly. Let's now take a look at how the adapter pattern works using a UML diagram. As you can see here, we have three key components: the client, which expects to interact with the target interface; the adapter, which implements the target interface and contains a reference to the adaptee class that has the incompatible interface. The adaptee is the existing class with an interface that the client needs to use but does not match the expected target interface. The adapter in this case converts calls from the client into calls that the adaptee can understand, enabling communication between the two. Let's see this in action with a simple C++ code example. Here we have a class oldPrinter that has a method oldPrint, but our system expects a printer interface with a print method. To solve this, we create an adapter class that implements the printer interface and internally calls the oldPrint method of the oldPrinter. This allows the client to use the oldPrinter without modifying the original code. You can see that the adapter works as a wrapper around the oldPrinter to make it compatible with the new interface. Next, we move on to the breach pattern. While the adapter focuses on making incompatible interfaces work together, the breach pattern is all about decoupling the abstraction of a system from its implementation. This means that both the abstraction and implementation can evolve independently, which makes the system more flexible. The classic example here is the relationship between a remote control and the devices it controls, whether it's a TV, fan, or air conditioner. The remote does not depend on the specifics of the device, but rather on an abstraction of the device behavior. You would use the breach pattern when you have a system where both the abstraction and the implementation need to evolve independently. A common use case would be when your system has different types of platforms or rendering technologies that need to work with the same abstraction. The bridge allows us to change the implementation without modifying the abstraction and vice versa. In the UML diagram for the bridge pattern, we have the abstraction class which defines the high-level control flow. The refined abstraction extends this abstraction. The implementer interface provides the low-level implementation details, and the concrete implementer class contains the actual implementation. The key point here is that abstraction and implementer are separate, allowing for independent evolution. You can swap or modify the implementation without affecting the abstraction layer, making your system more flexible and extensible. Let's look at a code example for the bridge pattern. In this case, we have a device interface that defines methods like turn on and turn off. The remote control class uses a reference to a device and can run it on or off. The beauty of the bridge pattern is that you can add new devices like fan or write without changing the remote control access. You can simply implement the device interface in new concrete classes. This separation ensures that changes to device behavior won't affect the remote control, and changes to remote control functionality won't require modifying individual classes. Let's now compare the adapter and bridge patterns side by side. The adapter pattern is used to make one interface compatible with another. It's generally used for integrating different pre-existing components. The bridge pattern, on the other hand, is used to decouple the abstraction from its implementation, allowing both to evolve independently. The adapter is typically applied after the system is built, while the bridge is usually applied during the design phase when you foresee future changes to either the abstraction or implementation. Here are some real-world examples to clarify these concepts further. Adapter pattern. Imagine you need to integrate a legacy payment system with a modern e-commerce platform. The legacy system uses a different interface for payment processing, and an adapter would allow the new platform to communicate with it without altering the legacy code. Bridge pattern. A good example of the bridge pattern is a graphics rendering engine. It could work with multiple rendering technologies like OpenGL, DirectX, or Falcon. The renderer abstraction is decoupled from the specific rendering technology, allowing you to add or change technologies without altering the engine's high-level logic. Now it's time for a quick hands-on exercise. For the adapter pattern, create an adapter for an old media player that can play audio files in a format that isn't natively supported by the modern system you are working with. For the bridge pattern, design a system where you can control different payment gateways like credit card and PayPal using a common abstraction. The key is to ensure that the payment methods are decoupled from the payment gateway logic. This exercise will give you practical experience applying these patterns. Let's recap what we have learned today. The adapter pattern makes incompatible interfaces work together without changing the original code. The bridge pattern separates abstraction and implementation, allowing both to evolve independently. Both patterns are powerful tools for maintaining flexibility, extensibility, and decoupling in your system designs. The key takeaways is that understanding when to apply each pattern will lead to cleaner, more maintainable, and scalable systems. For your homework, I recommend solving a few lead code design questions where you can apply either the adapter or bridge patterns. Additionally, read the relevant chapters from the Gang of Four book to gain deeper insights into these patterns and explore some advanced use cases. I'm looking forward to seeing how you apply these patterns in your projects. Thank you for your attention. Welcome to day 15 of our low-level design course. Today we are diving into two very important design patterns that are foundational for structuring and enhancing the flexibility of complex systems. These patterns are the composite and decorator pattern. Both of these fall under the structural design patterns category, and they help simplify relationships between objects and allow for more scalable and maintainable systems. In our next few slides, we will explore the problems they solve, their structure, real-world applications, and code implementations. Let's get started. Here's an overview of the agenda for today's lesson. First, we will start by revisiting what structural design patterns are so that we are aligned on their purpose and importance. Then we will focus on each of the patterns individually, starting with the composite pattern. We will define the pattern, look at its components, walk through a UML diagram, explore real-world examples, and see some code. After that, we will move on to the decorator pattern following the same steps. We will then compare the two patterns to see when to use each one and wrap up with an activity and homework. Let's dive in. Before we jump into the specifics of the composite and decorator patterns, let's do a quick recap on structural design patterns. These patterns focus on how objects and classes are composed to form larger structures. The goal is to simplify the relationships between objects and to make systems more flexible and easier to scale. We have already seen patterns like the adapter and the bridge that help us decouple classes, making them more reusable and easier to modify. Today, we will look at how the composite and decorator patterns enhance this flexibility by managing object relationships and responsibilities in a systematic way. The composite pattern solves a common problem in system design. How do we manage tree-like structures where we have both individual objects and groups of objects and treat them uniformly? For example, imagine a file system where you have both individual files and folders. A folder can contain files, but it can also contain other folders. How can we make sure we handle both files and folders in the same way without writing separate logic for each? That's where the composite pattern comes in. The composite pattern allows us to treat individual objects and compositions of objects in a uniform way. This is ideal when dealing with hierarchical structures or part-whole relationships like the aforementioned file system or a graphics editor. The key is that you can compose objects into tree structures that represent part-whole hierarchies. The advantage of this pattern is that it makes it easy to treat both simple and complex objects in the same way, reducing the complexity of our code and making it easier to maintain. The composite pattern has three primary components. Component. This is the common interface or abstract class that defines the operations. Both the leaf and composite will implement this interface. Leaf. This represents the individual objects that do not have any children. For example, in a file system, a file would be a leaf because it does not contain any other objects. Composite. This is a container that holds other components. It can contain both leaves objects and other composite objects, allowing us to build a tree structure. With these three components, we can create a hierarchical structure that makes working with both simple and composite objects seamless. Here's a UML diagram illustrating the structure of the composite pattern. Both the leaf and composite classes implement the component interface. The composite class has a collection of child components, which could be either other composites or leaves. This allows us to easily manage a tree structure where both types of objects can be treated the same way. Notice how the composite class can contain both types, facilitating recursive operations on the structure. Let's look at some real-world examples of the composite pattern. In a file system, files are leaf nodes, while folders are composite nodes that can contain other files or folders. This hierarchical structure allows us to interact with files and folders in the same way. In an organizational chart, individual employees are leaves, while managers or teams are composites that can contain more employees or other teams. In a GUI system, UI elements like buttons or text fields are leaves, while panels or windows are composites that can hold multiple UI elements. These real-world examples showcase how the composite pattern simplifies the management of complex tree-like structures. Let's now see some code for the composite pattern. In this example, we have a file system node base class. The file class is a leaf that represents individual files, while the folder class is a composite that can contain other file systems, whether they are files or folder. This allows us to treat files and folders uniformly, making it easy to display the file system structure. With this pattern, we can recursively perform operations like displaying the structure or calculating the size of the files. Now let's shift gears and talk about the decorator pattern. The decorator pattern solves the problem of how to add new behavior to objects dynamically without modifying their existing code. For example, imagine you have a car class and you want to add different features to the car, like a sunroof, leather seats, or advanced navigation. Instead of subclassing car for every combination of features, the decorator patterns allows us to add these features as decorators at runtime in a flexible way. The decorator pattern allows us to add new responsibilities to objects dynamically without altering their classes. It works by wrapping the original object in a decorator class that extends its functionality. This pattern adheres to the open-closed principle, which states that classes should be open for extension but closed for modification. Using decorators, we can add multiple functionalities to an object in a way that is both modular and flexible. The decorator pattern consists of three key components. Component. This is the common interface that both the original object and the decorator implement. Concrete component. This is the original object which we will decorate. Decorator. This is an abstract class or interface that wraps the concrete component and adds new functionality. Concrete decorator. This class extends the decorator and actually adds the additional behavior or functionality. By chaining multiple decorators, we can dynamically add different behaviors to the object. Here's the UML diagram for the decorator pattern. Notice that the concrete component represents the original object and the decorator class wraps it up. The concrete decorator extends the functionality of the component. This allows us to change decorators together to add multiple behaviors dynamically. Let's look at some real-world examples of the decorator pattern. Think about pizza ordering. A basic pizza is the original object, and toppings like cheese, olives, or mushrooms are decorators that add new functionality to the pizza. In a GUI system, consider a window that can have different features like a scroll bar or a border. Each of these features can be added dynamically using decorators. The input stream and buffered input stream classes in Java are an excellent example of this pattern. You can wrap an input stream in a buffered stream to add buffering functionality without altering the original stream. Here's a simple code example to illustrate the decorator pattern. In this case, we have a basic coffee class and we are dynamically adding features like milk or sugar using decorators. Each decorator wraps the original coffee object and adds functionality like adjusting the price or adding a description. This demonstrates how we can extend the functionality of an object without modifying its original code. Now let's compare the composite and decorator patterns. The composite pattern is used when you have a part-whole hierarchy. It allows you to treat individual objects and groups of objects uniformly. The decorator pattern is used when you need to add new behaviors to an object dynamically without modifying its class. The composite pattern is about structuring objects while the decorator pattern is about enhancing functionality. Both patterns are useful in different scenarios and understanding when to use each will make you a more efficient system designer. For today's hands-on activity, I would like you to implement a file system using the composite pattern. Create classes for files and folders and recursively display the structure of the file system. This will help you understand how to use this pattern in a hierarchical structure. As an extension, try building a coffee order system using the decorator pattern where you can dynamically add features to the coffee like milk, sugar, or flavoring. For homework, your task is to build a GUI widget system using the composite pattern. Represent elements like buttons, panels, and windows in a way that allows for easy composition. For the decorator pattern, implement a text editor where you can apply different text styles like bold, italic, and underline using decorators. To summarize today's lesson, the composite pattern allows us to simplify complex tree-like structures by treating both individual objects and groups of objects uniformly. The decorator pattern enables us to dynamically add new behaviors to an object without modifying its original code, making it flexible and scalable. Both patterns are important tools in your design toolkit, and knowing when and how to use them will allow you to create more flexible and maintainable systems. Thank you for your attention. Welcome to day 16 of our low-level design course. Today we are going to explore two important structural design patterns, the facade pattern and the flyweight pattern. These patterns are key in solving real-world software design challenges. The facade pattern helps in simplifying complex systems by providing a unified interface, while the flyweight pattern is designed to optimize memory usage by sharing common data across similar objects. So let's dive in and understand how these patterns work and when to use them efficiently. By the end of today's session, you will have a solid understanding of these two design patterns. We will explore the facade pattern, which is used to create a simple interface for complex subsystems, and the flyweight pattern, which helps in reducing memory usage by sharing common data. We will also look at practical applications, discuss UML diagrams, review code examples, and work through some hands-on exercises to solidify your understanding. Before we jump into today's topic, let's quickly recap what we mean by structural patterns. Design patterns deal with the composition of classes or objects. They are concerned with how the system's components fit together. The key idea here is composition over inheritance. That is, how we can compose objects and classes in a flexible way to create more complex structures. The two patterns we will cover today, facade and flyweight, are perfect examples of how structural patterns can improve system design by making it simpler, more maintainable, and efficient. Let's start with the facade pattern. Imagine you are interacting with a complex system, but all you need is a simple interface to get your work done. That's exactly what the facade pattern provides. It defines a high-level interface that makes a subsystem easier to use by hiding its complexities. The facade does not modify the subsystem, it just makes it easier for the client to interact with it. This pattern is particularly useful in large applications with multiple subsystems where you want to reduce the dependency between subsystems and client code. So why do we use the facade pattern? The main reason is to simplify the interactions between the client and the subsystem. Without the facade, the client would need to interact with multiple complex subsystems directly, which can be overwhelming. The facade provides a simplified interface and hides the complexities of the subsystem, reducing the learning curve for a new developer and simplifying code maintenance. It also helps in reducing tight coupling as the client is no longer directly aware of the subsystems it interacts with. Let's now look at some real-world examples of the facade pattern to understand how it works in practice. One classic example is a restaurant. As a customer, you don't need to know how the kitchen operates, what equipment is used, or how the food is prepared. All you need to do is place an order with the waiter who acts as a facade, providing a simple interface to the entire restaurant experience. Similarly, in a computer startup process, you press a single button and the operating system takes care of all the complex background processes like loading the OS, initializing drivers, and launching startup applications. Now let's take a look at the UML diagram of the facade pattern. In this diagram, you will see that the facade class provides a simplified interface to the client. The client communicates only with the facade, which in turn interacts with the various subsystems represented as separate classes in the diagram. The subsystems themselves are hidden from the client, making the system easier to use and maintain. Notice that the client is aware of the complexities of the subsystems, which is the primary benefit of the facade pattern. Here's a practical example. Let's say we are designing a home theater system. Without a facade, you would have to interact with various components like the DVD player, projector, speakers, and lights individually. But with the facade pattern, you could create a simple method called watch movie in the home theater facade class. This method would internally handle the interactions with all the subsystems, turning on the projector, dimming the lights, and starting the DVD player, all with a single call from the client. This greatly simplifies the client code and reduces the number of dependencies. Like all design patterns, the facade pattern has both pros and cons. The key advantages are its ability to simplify the client code by providing a single point of interaction and reducing the coupling between subsystems. However, the facade can also hide powerful subsystem features that may be useful to advanced users. Furthermore, a God facade may emerge if too many responsibilities are handled by the facade class, making it difficult to maintain and modify. It's important to find a balance and keep the facade focused on simplifying the core interactions, not handling everything. Moving on to the flyweight pattern, this pattern is all about optimizing memory usage when dealing with large numbers of similar objects. Instead of creating new objects for every instance, the flyweight pattern encourages the use of shared objects. These objects share common data, while unique data specific to each object is stored externally. This can significantly reduce memory consumption and improve performance, especially in applications with large datasets or systems that create a lot of similar objects. So why should we use the flyweight pattern? The primary benefit is memory optimization. Imagine a game with thousands of objects like trees, rocks, and buildings. If each object had its own unique data, the memory consumption would be massive. With flyweight, you can share common data across objects and store only the differences externally, drastically reducing memory usage. This pattern is particularly useful in graphics-heavy applications or large-scale systems where many objects are created with similar properties. Let's take a look at a couple of real-world examples where the flyweight pattern is used effectively. In a word processor, each character could be a separate object. Instead of storing the same font and style information for every character, the flyweight pattern allows all characters of the same font to share the font data, saving memory. Another example is in gaming, where many objects like trees and rocks share common characteristics like type or color, but differ in their position. These shared properties are managed by the flyweight, ensuring memory efficiency. Here's a UML diagram illustrating the flyweight pattern. The flyweight interface is the core of this pattern and defines the shared methods that all flyweight objects must implement. Each flyweight object stores only the shared intrinsic state. The extrinsic state, which varies for each object, is passed in by the client. This allows multiple objects to share the same flyweight data while maintaining their unique state externally. Let's look at a code example for the flyweight pattern. Imagine a chess game where each piece, like a king, queen, or pawn, has certain shared properties like color and type. These shared properties would be managed by the flyweight factory class, which ensures that only one object exists for each unique combination of shared properties. The position of the pieces on the board is the extrinsic state, and it can be passed in dynamically when needed. The flyweight pattern has several advantages. It significantly reduces memory usage, especially when dealing with large numbers of similar objects. However, it also introduces some complexity, particularly in managing the extrinsic state and ensuring that the correct shared objects are used. If not implemented carefully, the flyweight pattern can lead to code complexity and performance overhead in managing the object pool. Now let's move on to some hands-on mini exercises to apply what we have learned. For the facade pattern, I would like you to design an online shopping checkout system. The facade will simplify the interactions between subsystems like payment, inventory, and shipping. For the flyweight pattern, design a shape drawing app where different shapes like circles and squares share properties like color and type, while each shape's position and size are unique. Let's summarize the key takeaways from today's lesson. The facade pattern simplifies complex systems by providing a unified interface, hiding the internal complexity from the client. The flyweight pattern optimizes memory usage by sharing common data object, which is especially useful when working with large numbers of similar objects. Both patterns help reduce complexity and improve efficiency, but must be used carefully to avoid introducing additional challenges. Your homework for today is to design systems using three patterns. For the facade pattern, design a travel booking system that integrates flights, hotels, and car rentals under a simple unified interface. For the flyweight pattern, design a chess game where the pieces share data like color and type but differ in their position. Remember to keep things simple and apply the principles we discussed today. Before we end, here's a bonus insight. You will often find that the facade and flyweight patterns can be used together. For instance, in a game engine, the facade could simplify interactions with various subsystems such as rendering, input, and sound, while the flyweight pattern could be used to manage shared objects like terrain tiles, enemies, or characters, reducing memory usage and improving performance. Thank you for joining today's session. We have covered two essential design patterns, the facade pattern and the flyweight pattern, and explored how they simplify complex systems and optimize memory usage. Keep practicing these patterns and start implementing them in your own project. I look forward to seeing your designs and discussing them in our next session. Hello everyone and welcome to day 17 of our low-level design course. Today's session is going to be quite exciting. We will be covering two very powerful design patterns, the proxy pattern and the chain of responsibility pattern. These patterns are critical tools in a software designer's toolkit, helping us control access to objects, add behavior dynamically, and design flexible, scalable systems. We will not only learn the theory, but also look at real-world examples, relatable analogies, and of course, some hands-on coding. So let's dive right in. First up is the proxy pattern. Now think about situations where you might want to control access to an object. Maybe it's a large object that takes time to create, or maybe the object is remote, or perhaps you want to secure access based on certain permissions. A proxy stands between the client and the real object controlling the interaction. It provides the same interface as the real object, so the client does not even know whether it's talking to the real object or the proxy. This is a brilliant way to introduce flexibility, improve performance, or add additional layers of behavior without disturbing the original object. Proxies come in different flavors depending on the use case. We have the virtual proxy, which delays the creation of a resource intensive object until it's absolutely needed, saving systems resources. There's a protection proxy, which acts like a security guard, granting or denying access based on credentials or conditions. The remote proxy handles objects that exist in different address spaces. Think about calling a remote server object as if it were local. Finally, smart proxies can add logging, caching, or reference counting. Understanding the type you need is key to applying the pattern effectively in real-world scenarios. Let's make this even more relatable with a real-world analogy. Imagine using a credit card instead of directly getting cash from your bank. The credit card acts as a proxy. It lets you make payments without needing direct access to your bank account. Similarly, an ATM is a proxy for bank tellers. It allows customers to perform transactions without actually interacting with a human. The concept is simple: provide controlled, optimized, and often enhanced access to a resource without exposing the resource itself directly. Now let's peek into how the proxy pattern is structured. We usually define a common interface that both the real subject and proxy implement. The proxy holds a reference to the real subject and implements the same methods but can add logic such as checking access permissions, lazy instantiation, or logging. This way the client interacts seamlessly with either the proxy or the real subject without needing to know the difference. This separation of concerns makes our system more maintainable, scalable, and easier to extend. Here's a quick code snippet to solidify the concept. Suppose we have an image interface and two classes, real image and proxy image. The proxy image only loads the real image when the display method is called for the first time. This saves precious memory if the image is heavy and not always needed. This is a perfect example of a virtual proxy. Notice how the client code remains simple. It just calls the display method without worrying about whether the image was loaded already or not. Proxies are widely used in real-world systems and frameworks. Hibernate ORM uses proxy for lazy loading, only fetching objects when their properties are accessed. Spring AOP internally uses proxies to add cross-cutting concerns like logging, security, and transaction management. In a microservices architecture, API gateways act as remote proxies, handling authentication, request transformation, and routing. Even web browsers use smart proxies to cache resources, improving performance dramatically. Once you understand proxies, you will start seeing them everywhere in system designs. Alright, quick knowledge check. What is the primary responsibility of a virtual proxy? Is it access control, lazy instant initialization, logging, or security? If you picked lazy initialization, you are absolutely right. The virtual proxy focuses on delaying object creation until necessary, optimizing resource usage, especially when dealing with heavy, costly objects. Now let's move on to the chain of responsibility pattern. This pattern is all about processing a request through a chain of handlers. Each handler decides either to handle the request or pass it along to the next handler in the chain. The big advantage here is loose coupling. The sender of a request does not need to know which receiver will handle it. This makes the system highly flexible and dynamic. You can add, remove, or rearrange handlers without changing the client code. To bring this to life, think about a customer service center. You first reach a level 1 support executive. If they can't solve your issue, it gets escalated to level 2, then to a manager if necessary. Each level decides, can I handle this? If yes, done. If not, pass it onward. Similarly, in software, web frameworks use chain of filters or middleware to process incoming requests in a modular, clean way. In a chain of responsibility structure, we define an abstract handler class with a reference to the next handler. Each concrete handler implements the request handling logic and, if unable to process, passes it along to the next handler. This allows us to build flexible, dynamic processing pipelines. The client just initializes the chain, it does not have to worry about the inner details of how the request is handled. For example, imagine an application with a request approval workflow. You can have different handlers, manager, director, vice president, each checking if they have enough authority to approve a purchase. If a manager can't approve a high value purchase, the request moves up to the director and so on. The handlers are decoupled and the chain can be adjusted easily without modifying the request initiator. The chain of responsibility pattern is used extensively in modern software. In Java, servlet filters form a chain to pre-process requests, checking authentication, logging, etc. before the servlet even runs. In Node.js and Express, middlewares form a chain that each HTTP request passes through. Even event handling in web browsers, when you click something, the event bubbles up through a chain of handlers, giving multiple elements a chance to respond. Clearly, mastering this pattern opens up tremendous design possibilities. Now it's time for you to get your hands dirty. For today's exercise, try creating an authentication system using a chain of responsibility. First, check the password. If it's valid, then check the OTP. If that passes, check a captcha. Each step should be separate handler in the chain. As a bonus, implement a proxy for a large file download, ensuring that the file is only fetched from the server when someone actually requests it. Real practice will cement these patterns into your thinking. Let's recap today's session. The proxy pattern gives us a smart way to control access to real objects and optimize system performance. The chain of responsibility pattern decouples the sender and receiver, letting a request travel flexibly through a chain until it's handled. Both patterns improve the scalability, maintainability, and clarity of your system. Understanding these patterns will help us craft designs that are both elegant and powerful. For homework, I highly recommend you to go through the proxy and chain of responsibility chapters in the Head First design patterns. Also try applying these patterns to your parking lot LLD project. Maybe use a proxy to manage parking ticket generation or chain of responsibility for access control levels in the parking lot. Exploring these ideas will deepen your understanding and truly prepare you for real-world system design challenges. Thank you for your attention. Hello everyone and welcome to day 18 of our low-level design course. Today we are diving into two powerful behavioral design patterns that are heavily used in real-world systems, the command pattern and the mediator pattern. Understanding these patterns will not only improve the flexibility of our systems, but also make our code much cleaner, modular, and easier to extend. Let's get started. By the end of today's session, you should be very comfortable with both the command and mediator patterns. We will first understand what problems they solve. Then we will look at how they are structured, explore their key components, and walk through relatable real-world examples. Finally, we will practice designing using these patterns so you can apply them confidently in your own projects. Quick refresher before we go deeper. Behavioral patterns are all about how objects communicate and collaborate to perform tasks. They define not just what objects do, but how they interact with each other. Think of it like the rules of communication inside a big team. Good interaction makes teamwork smoother, bad interaction creates chaos. Command and mediator patterns are two ways to manage these communication rules smartly. Let's start with the command pattern. Imagine you want to issue a request like turning on a light, but you don't want the object sending the request to know the internal workings of the light. In the command pattern, we treat requests as objects. This gives us tremendous flexibility. We can delay a request, queue it, undo it, and even compose complex operations, all without changing the original code. The command pattern has a few important building blocks. First, there's the command interface, which defines an abstract method like execute. Then we have concrete command classes, where we implement specific actions like turn light on or turn light off. The receiver is the actual object that performs the action, like the light or fan. The invoker triggers the commands when needed without knowing the exact details. And finally, the client wires everything together. It knows which command to associate with which receiver. The advantages of the command pattern are huge. First, it decouples the sender from the receiver, meaning we can change either independently. Second, it naturally supports operations like undo, redo, logging, or patch execution. And third, it makes the system easily extensible. Adding new commands does not affect the invoker or existing clients. It's a very flexible and scalable design choice. Here's, Here you can see the UML diagram for the command pattern. Notice how the client sets everything up. It creates commands, assigns receivers, and passes commands to the invoker. The invoker simply calls execute on the command object. It does not know or care what the command is actually doing. This keeps the system beautifully decoupled. Let's look at a few real-world examples. A TV remote is a perfect illustration. Pressing a button sends a command to the TV without the remote needing to know how the TV processes that request. Similarly, in a text editor, pressing Ctrl Z triggers an undo command. Or think about a task scheduler that queues tasks and executes them later. Each task is simply a command. Imagine you are designing a smart home remote control. You have devices like lights, fans, and thermostats. Each action, turning a light on, setting the temperature, can be encapsulated in a command. The remote control just triggers the command without knowing what device it is actually controlling. This separation makes the system so much easier to modify and extend in the future. Now moving on to the mediator pattern. In complex systems, classes often end up directly depending on each other, creating a web of dependencies that's very hard to manage. The mediator pattern solves this by introducing a middleman, the mediator, which controls and coordinates communication. Instead of objects talking directly to each other, they send messages to the mediator. In the mediator pattern, we define a mediator interface which outlines how communication happens. The concrete mediator implements this interface and contains the logic for coordinating interactions. Each colleague object, like a user in a chat room or a plane in an ATC system, interacts only with the mediator, not with other colleagues directly. This separation makes the system much simpler and easier to maintain. The biggest advantage of the mediator pattern is reduced coupling. Instead of having every object talk to every other object, leading to tangled, hard to maintain code, you centralize all communication in one place. This improves scalability, eases debugging, and makes future changes much safer and faster. Here's the UML for the mediator pattern. Notice how all colleague objects interact only with the mediator and not with each other. The mediator acts as a single hub through which all communication flows. This architecture dramatically reduces complexity as the number of objects grows. We have already interacted with mediator patterns without realizing it. Think about a chat room. You send a message to the chat room server, not directly to another user. In air traffic control, planes don't talk to each other. They communicate via the ATC tower. Even in GUI frameworks, buttons, text, fields, and drop-downs often communicate via centralized event handlers or mediators. Let's imagine a basic chat room. Each user, called a participant, registers with the chat room mediator. When one participant sends a message, they call the chat room's send method and the chat room forwards the message to the appropriate recipient. This design makes adding new users easy without needing to modify existing code. Now it's time for you to try. Design a smart home controller using the command pattern. Your system should include devices like lights, a thermostat, and a security system. You will need to define commands for actions like turn on, turn off, and set temperature. Focus on achieving complete decoupling between the remote control and the devices themselves. Similarly, practice designing an air traffic control system using the mediator pattern. Each plane will act as a colleague object and the ATC tower will be the mediator. Planes should not communicate with each other directly, only via the tower. The tower will coordinate when it's safe for each plane to land or take off, avoiding collisions. Your homework challenge is a little bigger today. Design a text editor that supports undo and redo using the command pattern. Each editing action, typing, deleting, formatting should be encapsulated as a command. If you want a bonus challenge, create a chat application where users communicate via a mediator. Both exercises will give you deep hands-on mastery of these two patterns. Let's summarize. Today we learned the command pattern helps us wrap a request into an object, giving us powerful control over execution, queuing, and undo. We also saw that the mediator pattern centralizes communication among objects, reducing messy dependencies and making systems easier to grow and maintain. Both patterns are vital tools in a designer's toolkit. In our next session, we will explore the observer pattern and the strategy pattern, two patterns that are crucial when building systems that interact with changes dynamically. Trust me, you will use them all the time once you master them. See you in the next class and thank you for your attention. Hello everyone and welcome to day 19 of our low-level design journey. Today we are going to dive into two of the most powerful and widely used design patterns, the observer pattern and the strategy pattern. Understanding these patterns will not only help you design more flexible and maintainable systems, but also prepares you for real-world coding interviews and projects. So grab your notes and let's get started. Before we dive deep, let's take a moment to understand what we aim to achieve today. First, we will thoroughly understand how the observer pattern works, its components, and where it shines the most. Then we will explore the strategy pattern, how it helps us deal with changing behaviors dynamically. After that, we will apply these patterns through hands-on mini projects to ensure we can practically use them. By the end of today's session, we will not only know the theory but also have built working examples. Let's go. Let's begin with the observer pattern. The core idea behind this pattern is simple yet powerful. When one object's state changes, all its dependents should be automatically notified and updated. This establishes a one-to-many relationship between objects where the one is called a subject and the many are observers. This pattern is crucial in event-driven programming where different parts of a system must react to changes elsewhere without being tightly coupled together. Now let's break down the main components involved in the observer pattern. First, we have the subject. This object holds the state and maintains a list of observers. It provides methods to add, remove, and notify observers. Next, the observer, an interface or abstract class that defines the update method, which is called when the subject changes. Then comes the concrete subject, an actual implementation of the subject interface containing the real business logic and state. And finally, concrete observer. These are specific implementations of the observer that update themselves when notified. By separating these responsibilities, we achieve low coupling and high flexibility. You might be wondering, when should we actually use the observer pattern? The answer lies in any situation where multiple parts of a system need to stay synchronized with some central data. It's a perfect fit for event-driven architectures such as chat applications where new messages trigger UI updates, or financial apps where stock prices update across multiple dashboards. Other classic examples include notification systems, real-time gaming leaderboards, and weather monitoring applications. Whenever you have a change that should ripple across multiple dependent objects, Observer is the way to go. Here's a simplified UML diagram representing the observer pattern. As you can see, the subject maintains a list of observers, and when an event occurs, it notifies all of them, calling their update methods. This setup creates a clean, scalable architecture where subjects and observers can evolve independently, promoting a highly modular system design. Moving on to the strategy pattern, this pattern is all about behavior encapsulation. It allows a class behavior to be selected at runtime. Instead of using conditionals like huge if-else blocks to choose behaviors, we delegate the responsibility to different strategy classes. Each strategy encapsulates an algorithm, and the context class simply delegates the work without worrying about which specific strategy is being used. This separation of concerns makes the system more flexible and extensible and testable. Now let's understand the building blocks of the strategy pattern. First, the context class, which contains a reference to a strategy object and delegates it to perform a specific task. Then the strategy interface or abstract class. It defines a family of algorithms but lets the actual implementation vary independently. Finally, concrete strategies. These are specific implementations of different algorithms or behaviors. Using this approach, the context does not need to know the details of each behavior, promoting open-closed principal compliance, open for extension, closed for modification. When should we reach out for the strategy pattern? Think of situations where you have multiple algorithms or behaviors that you might need to switch between at runtime. Common examples include switching between different payment gateways, choosing between different file compression algorithms, or deciding among different sorting mechanisms. Rather than cluttering your context class with complicated if-else or switch statements, the strategy pattern allows you to clearly plug in new behaviors with minimal changes. Let's take a look at the strategy pattern UML. Notice how the context holds a reference to the strategy interface, not to a specific strategy implementation. This allows us to change the algorithm dynamically by simply setting a new strategy object without touching the core logic inside the context class. It's an elegant and scalable solution for behavioral flexibility. Time to put theory into practice. In the first mini project, you will create a weather station application using the observer pattern. The weather station will act as the subject and track temperature changes. The display units, our observers, will subscribe to the weather station and get automatically updated when the temperature changes. This exercise will give you a solid grasp of real-world event-driven programming. Next, using the strategy pattern, you will build a simple payment system. Here, the payment service will serve as the context, while payment strategy will define different payment algorithms. You will create concrete strategies for credit card, PayPal, and wallet payments. Depending on the user's choice, the system should switch between different payment methods seamlessly without any messy conditions. Before we wrap up the concepts, let's engage in a thoughtful discussion. First, consider how exactly does the observer pattern help us achieve loose coupling. Then think about strategy pattern versus if-else statements. What trade-offs do you see? Finally, can you think of scenarios where combining the observer and strategy patterns could lead to even better system designs? Reflect on this, they will sharpen your system design intuition for interviews and real-world work. As you conclude today's session, make sure you complete your deliverables. Submit your two mini projects, the weather station build using the observer pattern and the payment system build using the strategy pattern. Additionally, write a brief reflection summarizing your experiences, challenges faced, and lessons learned during the projects. This reflection will deepen your learning. Here are a few pro tips to help you master these patterns. First, leverage the observer pattern. Whenever you are designing scalable notification-based systems, it pays off massively as system grows. Second, use the strategy pattern whenever you see growing complexity in decision-making logic. It will keep your code clean and extensible. And most importantly, confidently talk about these patterns during interviews. If you can explain not just what they are, but when and why to use them, you will truly stand out as a design-focused engineer. Thank you for your attention. Hello everyone and welcome to day 20 of our low-level design course. Today's session is particularly exciting because we will be learning two behavioral design patterns that are extremely powerful in real-world software development, the template method and the state pattern. By the end of this session, you will be able to identify real scenarios where these patterns shine and even implement them with confidence. So let's dive right in. Before we start, let's get clear on our goals for today. First, we will thoroughly understand the template method and state patterns, how they work and where they are used. Second, we will see how to apply them to real-world software design problems, not just theoretically, but practically. And lastly, we will practice implementing these patterns through UML diagrams and code examples. This structured approach will help you not just learn, but truly internalize these design concepts. Just to quickly set the context, remember that behavioral design patterns are all about how objects interact with each other and how responsibilities are distributed. They are different from structural patterns, which are about how classes are composed, and from creational patterns, which are about object creation. Behavioral patterns like template method and state focus on the flow of control and dynamic behavior in our applications. Today's patterns will empower your code to be more adaptable and resilient. Let's start with the template method pattern. Imagine you have an algorithm or a workflow that should remain consistent in structure across multiple classes, but where a few specific steps vary. Instead of duplicating the overall logic in each class, we define a template, a base method that sets the steps in order. Subclasses can then fill in the specific behavior by overriding only those parts that differ. This promotes both code reuse and consistent execution flow. A simple but powerful real-world example is making coffee or tea. The process looks like this. First, you boil water, then brew the drink, pour it into a cup, and finally you add condiments. While brewing coffee and tea involve different processes, steeping tea leaves versus dipping ground coffee, the high level steps remain exactly the same. That's the essence of the template method. Fix the structure, allow flexibility where needed. Looking at the technical side, the abstract class defines a method that calls several operations in sequence. This method is our template. Some operations are implemented directly into the abstract class, but crucial ones are left as abstract methods, meaning subclasses must implement them. This gives a nice balance of fixed flow and customizable steps. In the next slides, we will look at UML diagrams to make this even clearer. Here's a quick Java example to bring it to life. The abstract class caffeine beverage defines a method called prepare recipe. This method outlines the sequence boil water, brew, pour, add condiments. But the brew and condiment methods are abstract, allowing subclasses like tea and coffee to fill in the specifics. Notice how subclasses focus only on the differences. They don't worry about the boiling or pouring steps. Now, when should you use the template method pattern? Anytime you have a set of classes that share a similar sequence of operations, but where certain steps might be different across implementations. It eliminates code duplication, enforces a uniform structure, and promotes cleaner, more maintainable code bases. It's especially useful in frameworks, SDKs, or anywhere you are providing a customizable workflow. Alright, let's pause here for a quick 10-minute break. Use this time to stretch, grab a cup of coffee or tea, maybe even observe the template method in action at your coffee machine. We will regroup shortly to explore the state pattern. Welcome back. Let's switch gears and explore the state pattern. The state pattern allows an object to alter its behavior when its internal state changes. It's like the object's class itself changes at runtime, although technically it's the behavior that changes, not the class. Imagine using an ATM. When you approach it without inserting your card, it prompts you to insert one. Once you insert your card, it transitions to a card inserted state and asks for your PIN. After entering the correct PIN, it transitions again and allows you to perform operations like cash withdrawal. Each state, no card, card inserted, authenticated, controls the available operations. That's the magic of the state pattern. Behavior changes based on the object's state. From a technical perspective, the state pattern has three core elements: the context, which holds a reference to the current state, the state interface, which defines the behavior, and the concrete states, which implement specific behaviors for each state. When the context's internal state changes, it simply delegates to a new concrete state without altering the code's logic flow. Extremely powerful. Let's look at a Java code example. Here we define a state interface with actions like insert card, eject card, enter pin, and withdraw cash. We then have a class like noCardState implementing the state interface. When you call insert card on the context in this state, it responds appropriately, maybe transitioning to the hash card state. The important takeaways is the context delegates behavior to the state object. This removes all the complicated if-else or switch logic you would otherwise write inside the context class. You should use the state pattern when the behavior of an object depends heavily on its internal state, and it's cleaner to represent each state as a separate class. It prevents bloated, hard to maintain code that's filled with multiple conditions. It's perfect for systems like vending systems, elevators, game levels, or any scenarios where an object's behavior must change dynamically. Let's apply what we have learned. Think about a traffic light system that states are red, yellow, and green. Sketch the context and the three different states. Try to model how transitions would happen and how behavior changes. For example, at green, allow traffic; at yellow, slow down; at red, stop completely. To wrap it up, the template method pattern is all about defining a structure once and allowing subclasses to tweak specific parts. It encourages code reuse and standardization. The state pattern, on the other hand, helps us manage dynamic behavior changes without messy conditionals. It enables clean separation of concerns, making code easier to extend and maintain. Both are essential tools for building flexible, maintainable, and professional grade software. For practice tonight, try designing a food delivery flow using the template method. Define the overall delivery process and allow different types of orders to customize steps. Also, model a washing machine's operational states using the state problem. Think about washing, rinsing, spinning, and how the machine should behave differently in each mode. That brings us to the end of today's session. Thanks for staying engaged and participating actively. Remember, understanding patterns deeply is a gradual process. Don't just memorize, practice applying them to small systems you design. Thank you for your attention. Hello and welcome everyone to day 21 of our low-level design course. Today is going to be a very important day as we are going to learn three extremely useful design patterns: the visitor pattern, the iterator pattern, and the momento pattern. These patterns are not just theory, they are used every day in real world systems, whether it's applying discounts, navigating playlists, or implementing undo features in applications. So let's get ready to dive deep and strengthen our design toolkit even further. Before we get into the patterns, let's first look at today's roadmap. We will start by understanding why these patterns are important, setting the foundation first. Then we will dive individually into the three patterns. First, the visitor pattern, which helps us apply new operations to objects without modifying their structure. Next, the iterator pattern, which gives us a way to traverse data collections without exposing how they are implemented internally. And finally, the momento pattern, which helps us capture and restore object states, a must-have for features like undo. After covering each, we will also do a quick comparison, followed by a mini exercise to apply what we have learned, and finally we will summarize everything. So why do we need these patterns in the first place? Let's think practically. Suppose we have an application with hundreds of product types and tomorrow we want to add a new pricing strategy. Do we want to modify every product class? That's probably not. Here's where the visitor pattern saves us, allowing us to apply operations externally. Similarly, when you are scrolling through a Spotify playlist, you don't really care how songs are stored. You just want a smooth experience of moving from one song to the next. That's where the iterator pattern becomes critical. And what about undo and redo in applications like Word? Imagine writing 20 pages and then wanting to roll back 5 edits. We need a way to save checkpoints, and that's exactly what the momento pattern gives us. Each of these patterns addresses real engineering problems, not just academic ones. Let's start with the first pattern, the visitor pattern. At its core, the visitor pattern is about separating an algorithm from the object structure it operates on. Imagine you have a set of different objects, say various types of products, electronics, groceries, and so on. You want to apply operations on these objects like calculating discounts or taxes. Instead of modifying every class whenever a new operation is needed, you externalize the operation to a new visitor class. This follows the open-closed principle. Our objects are open for extension, meaning we can add new operations easily, but closed for modification, meaning we don't touch existing code, thereby avoiding breaking things. This pattern shines especially when the structure of objects remains stable, but the operations keep evolving over time. Let's bring this closer to reality with an example. Think of an e-commerce platform like Amazon. You have multiple product types: electronics, groceries, clothing, furniture. Each category might have different tax rules. Electronics might have 18% tax, groceries might have 5%. Now, should each product class know how to calculate its tax? Ideally, no. Instead, we create a text visitor class that knows how to visit each product and calculate the approximate tax. This way, if tomorrow a new tax rule is introduced, say COVID surcharge, we simply add it to the visitor without modifying the product classes at all. Here's what the code structure looks like. We define an interface called visitor, where each method handles a different product type. Each product class, like electronics and groceries, implements an accept method. When we call accept, the visitor gets a chance to operate to the product without changing the product's own code. This makes the system very flexible and future-proof. Now the important question: when should you use the visitor pattern? First, when new operations need to be added frequently. Second, when the object structure itself is relatively stable. And third, when you want to comply with the open-closed principle by keeping your classes unchanged and externalizing new behaviors. But remember, if your object structure changes frequently, the visitor pattern might add complexity, so use it wisely. Next up is the iterator pattern. The goal of this pattern is simple but powerful. It allows to access elements of a collection one by one without knowing how that collection is implemented internally. You can think of it like providing a common remote control to navigate through different collections, whether it's an array, a linked list, or even a tree structure. Let's again relate it to real life. Imagine you are using a Spotify playlist. When you hit next or previous, do you care how Spotify stores your songs? Absolutely not. Behind the scenes, it could be a dynamic array, a linked list, or something entirely custom, but you as a user interact through a simple interface. Play next song, play previous song, shuffle songs, and so on. That's exactly the beauty the iterator pattern provides in software design too, a clean way to move through data. Here's how we do it technically. We define an interface called iterator with two methods, hasNext to check if there are more elements and next to fetch the next item. Then any collection like a song collection can provide its own implementation of iterator. This way the user can navigate through the songs without worrying about whether it's stored in a list, a queue, or anything else. You should use the iterator pattern when you want to decouple the way a collection is stored from how it is traversed. You expect multiple types of collections and still want a unified way to access them, or you want to allow multiple simultaneous traversals like forward and backward on the same dataset. Iterator makes collections flexible and extensible. Now let's move to our third pattern for today, the memento pattern. And this one is a favorite for applications needing undo or rollback functionalities. The memento pattern allows you to capture an object's internal state, store it outside, and restore it later without violating encapsulation. The key here is the object that saves the state, originator, the object that stores the state, memento, and the object that manages saving and restoring, caretaker. Let's look at some real-world examples, undo and redo in Microsoft Word. Every time you make a change, Word captures a snapshot of the document. When you hit undo, Word restores a previous snapshot from history. In gaming, saving checkpoints is another brilliant example. Games like Call of Duty or Zelda allow players to save their progress, so if they fail, they don't start from the beginning, but resume from a checkpoint. Both of these functionalities depend heavily on the principles of the memento pattern. Technically, here's how it looks. We create a text editor with methods like setText to edit and methods like save and restore to create and apply snapshots. The memento object acts like a hidden snapshot, preserving previous states without exposing or tampering the internal workings of the text editor. This pattern ensures separation of concerns, making the system safe and clean. Use the memento pattern when you need undo or redo features. You want to checkpoint an object's state, or you want to implement state recovery after failures without breaking encapsulation. It's highly useful for text editors, gaming systems, and even financial applications where rolling back transactions safely is critical. Now let's bring it all together. Visitor pattern, use it to add new operations without modifying objects. Iterator pattern, use it to traverse collections without worrying about their internal structure. Memento pattern, use it to save and restore object states cleanly and safely. Each pattern addresses different problems, but together they make your systems more flexible, resilient, and easy to extend. Time for a quick challenge. Think of a drawing app where a user can create shapes, circles, rectangles, lines. Now implement undo functionality. How would you do that? Use the memento pattern. Each time a user draws, save a snapshot of the canvas. When they press undo, restore the previous snapshot. Give it a try after the session. Today we covered how the visitor pattern lets us add behavior externally, how the iterator pattern simplifies traversal, and how the memento pattern provides powerful state recovery mechanism. Each of these patterns bring a new level of power and control to your low-level designs. Now it's your time for your questions. Feel free to ask about where and when to use these patterns. Share examples you can think of or clarify any doubts you have. about today's session. That's it for today's session. In our next session, we will continue expanding our design skills with the template method and state prop patterns. Thank you so much for your attention and keep practicing. Great designers are made through real-world applications. Welcome to day 22 of our low-level design journey. Today marks a significant milestone as we will be working on our first major pattern integration project. Our goal is to combine multiple design patterns we have learned so far into a cohesive real-world system, a notification system. We will focus on three critical aspects of software design: extensibility so that the system can grow easily, maintainability so that it remains easy to understand and change, and scalability to ensure that it can handle growing loads smoothly. Let's dive deep and make all our learnings so far come to life. Let's start by truly understanding the problem we are going to solve. Imagine we are building a notification system for a product like Amazon or Uber. Notifications must be sent via multiple channels: email, SMS, push notifications, even WhatsApp. Different types of notifications need to be handled: alerts, reminders, promotions. Crucially, the system should allow easy addition of future channels like Slack or Microsoft Teams without needing to rework the core design. Moreover, the system must be reliable. If a notification fails, it should automatically retry. And since we could be sending notifications to millions of users, the system should efficiently handle bulk operations. Finally, business logic like payment or booking should remain decoupled from notification mechanisms. This is the real world problem we are solving. Design patterns are tools in our toolkit, and depending on the requirements, we carefully pick the right ones. For dynamic creation of different notification types, we will use the factory pattern. To ensure reliable delivery, especially if the first attempt fails, we will introduce a command pattern combined with a retry mechanism. To decouple notification logic from business logic, we will use the observer pattern so that business components can simply raise an event and not worry about how notifications are sent. To efficiently create multiple similar notifications, say for a promotional blast, we will use the prototype pattern. When we need to dynamically add behaviors like encrypting a message before sending, the decorator pattern fits perfectly. And to hide the complexity behind a simple interface for clients, the facade pattern will serve us well. Always remember, good design is about choosing the right patterns to solve the right problems. Now let's zoom out and look at the system's architecture. We are building an event-driven system, meaning notifications are triggered by events like payment success or new friend request. These events trigger the event manager, which then notifies the relevant observers. Notification commands are queued separately from the main application flow, making the system asynchronous and resilient. The factory dynamically creates the right type of notification based on configuration. Finally, the notification manager, acting as facade, gives client code a clean, easy to use try entry point without worrying about what happens internally. This separation of concerns ensures our system remains scalable, maintainable, and testable. Let's now break down the key components we will be building. First, we define a notification interface that all specific notification types, email notification, SMS notification, push notification will implement. The notification factory will handle the logic of deciding which notification object to create at runtime. The notification service will handle sending logic and manage retries. The notification manager, serving as a facade, will provide a simple API for clients to request notifications. We will also implement a notification command class to encapsulate sending logic along with retry strategies. And finally, the user event manager will handle business events and trigger observers that generate notifications. All of these components will work together like a well-oiled machine. Here's how everything fits together in runtime. First, a business event occurs, such as a successful payment or order placement. The event manager detects this event and notifies all registered observers. Each observer responsible for a specific notification channel or type creates a notification command and places it into a command queue. A separate notification processor pulls commands from the queue and, using the factory, creates and sends the appropriate notifications. This architecture keeps our business services fast and responsive as notification sending happens asynchronously. Now it's time for you to apply everything we have discussed. Start by implementing the notification interface along with its concrete classes like email notification and SMS notification. Next, build a factory that can dynamically create notification instances based on input type. Then implement an event manager that allows observers to register and receive events. Introduce command classes to encapsulate send logic and retries. Finally, bring all this together under a notification manager that acts as a facade. Remember, focus on writing small, single responsibility classes that are easy to extend later. As you design, keep these critical best practices in mind. Always adhere to open closed principle. Your system should be open for extension but closed for modification. Respect the single responsibility principle. Each class should have one clear focused job. Design for extensibility by anticipating future channels like WhatsApp, Slack, or even voice calls. And finally, focus on testability. Make sure retry logic factories and services can be unit tested independently. These practices will make your system future proof and significantly reduce bugs and maintenance costs. Here's a quick mini assignment to test your design. Add a new channel, WhatsApp notifications into your system. Observe, did you need to change existing classes or could you simply add new ones? How easy was it to update your factory? Were your observers able to handle the new type cleanly? This exercise will reveal if your design is truly flexible and extensible or if it needs further refinement. To wrap up, remember this key lesson. In real-world systems, multiple patterns are often used together to meet diverse requirements. Designing for extensibility and decoupling from day one saves massive headaches down the road. In today's project, we combined factory, observer, command, and facade patterns to build a notification system that is scalable, maintainable, and resilient. Keep practicing pattern integration. It's the difference between being a good designer and a great one. Finally, let's look at the UML diagram summarizing today's work. You will see the notification interface and its concrete implementations like email and SMS. You will also notice the notification factory responsible for dynamically creating these objects. Commands are used to queue sending actions reliably. The observer system cleanly separates business events from the notification system itself. Study this guide diagram carefully. It's a blueprint for building robust, real-world, event-driven system. Thank you for your attention.